Welcome to the course on two-phase flow with phase change in conventional and miniature channels. I am Manmohan Pandey, Professor of Mechanical Engineering at Indian Institute of Technology, Guwahati. So, what is two-phase flow and what is two-phase flow with phase change? What are conventional channels and miniature channels, and that we will discuss today, and then we will introduce notation for two-phase flow. So, what is two-phase flow? As the name suggests, when two phases are flowing together, it is two-phase flow. Matter commonly exists in three phases: solid, liquid and gas. So, if any two phases are flowing together, it should be called two-phase flow. For example, solid and liquid flow commonly occurs in slurries, and if it is solid and gas flow, that is also two-phase flow. It is found in pneumatic transport and fluidized beds in the industrial applications. Then there is liquid and gas flow. This is quite common in industrial applications when a liquid and a gas are flowing together. For example, air and water flowing together in a pipe. In this course, we will be concerned mostly with liquid gas flow. Also, when there are two immiscible liquids flowing together, that is also sometimes referred to as two-phase flow. For example, oil and water flowing together in a pipe, that is also called two-phase flow, although strictly speaking it is not a two-phase flow, but a two-component single-phase flow. So, as I said earlier, in this course we will be mainly concerned with the flow of liquid and gas, and the two-phase flow can be with or without phase change. For example, if it is air and water flow, then air cannot become water and water cannot become air. So, it will remain a two-phase flow without phase change. But if it is steam water mixture flowing in a pipe, then steam can condense into water or water can evaporate into steam. So, therefore, it will be two-phase flow with phase change, or at least there is a possibility of phase change. So, in this course, we will be concerned with both two-phase flow without phase change and with phase change also. There is a classification of conventional and miniature channels based on the different physics of the flow. In small channels, different effects are important. In conventional channels, different effects are important. So, therefore, the smaller channels, two-phase flow in smaller channels has to be studied in a different way. There is a characteristic length called Laplace length scale, which is defined as follows. Here sigma is the surface tension, g is the acceleration due to gravity, and delta rho is the density difference. Okay. So, this delta rho, this is equal to rho L minus rho G, the density of liquid minus the density of gas. Usually, rho L is much larger than rho G in two-phase flow mixtures. Actually, this represents the relative strength of the surface tension effect with respect to the buoyancy effect. If the hydraulic diameter is larger than the Laplace length scale, then it is called conventional channel. And otherwise it is called miniature channel. Okay. There is a non-dimensional number called bond number. It is defined as G delta rho dH square upon sigma. Bond number. Okay. And we can rewrite it as dH square upon lambda L square. Okay. Or we can write square root of bond number is equal to dH upon lambda L. Okay. So, there is a classification in which if bond number is less than or equal to 0.3, then it is called mini channel. What does it mean is that if bond number is small, then it means that the relative strength of the buoyancy effect is less than that of the surface tension effect, and buoyancy effect becomes negligible if the square root of bond number is less than or equal to 0.3. So, in that case stratified flow becomes impossible. We will discuss later different types of flow regimes. Stratified flow is that in a horizontal pipe, in that liquid stays in the lower part of the pipe and gas stays in the upper part of the pipe, and the two phases are segregated. So, that type of flow is not possible if the channel is very small and the bond number square root of that is less than 0.3. Sometimes instead of the bond number or the Laplace length scale, an absolute classification is used. Microchannels are defined as those channels for which the hydraulic diameter is in the range of 10 to 100 micron, and then there are mini channels for which hydraulic diameter is in the range of 100 to 1000 micron or 1 millimeter. Then mesochannels have diameter of 1 to 3 millimeter, and conventional channels they have hydraulic diameter greater than 3 mm. Okay. Now, we will introduce notation for two-phase flow. Suppose a two-phase mixture is flowing through a pipe and there is liquid and gas here. Mass flow rate m dot g, suffix g and suffix f we will use for the gas and the liquid. Suppose the area is AG and AF. The area through which gas flow is flowing is AG and the area through which liquid phase is flowing is AF. Actually, the phases will not always be segregated like this. There will be different types of flow patterns, but this is just a schematic. So, the total area of the cross section occupied by the gas phase is Ag, and the total cross sectional area occupied by the liquid phase is Af. But the shapes of these areas can be different in different flow patterns. Then there is a quantity which is denoted by alpha. A is the total area of cross section, and 1 minus alpha will be equal to Af upon A. Ag plus Af is equal to A. Okay. And this is called the void fraction. And here the axial coordinate will be denoted by Z, and the velocities of the phases will be denoted by Ug and Uf. The mass quality is defined as x is equal to mass flow rate of the gas upon mass flow rate of liquid plus mass flow rate of gas, total mass flow rate, and 1 minus x is equal to mass flow rate of liquid upon total mass flow rate. Okay. So, from here we can say that the mass quality has to be between 0 and 1. 0 mass quality means that it is only liquid, and mass quality 1 means it is only gas, and if it is between 0 and 1, then it will be a two-phase mixture. There is another quality which is called thermodynamic equilibrium quality, and it is denoted as X equilibrium. It is defined as H minus Hf upon Hfg. Hf is the enthalpy of the saturated liquid at the existing pressure, and Hfg is the latent enthalpy of vaporization. The suffix Fg means the difference between the gas and liquid properties. So, Hfg is equal to Hg minus Hf. Okay. Now, this thermodynamic equilibrium quality can be less than 0, that is negative, or it can be greater than 1 also. If it is less than 0, then it means subcooled liquid. And if it is 0 to 1, then it is saturated liquid plus vapor. Here we are considering a two-phase mixture of the same substance, so there can be phase change. Of course, here the limiting case is X equilibrium quality equal to 0 and equilibrium quality equal to 1, they mean single phase liquid and single phase gas, the saturated liquid and saturated gas. Then if X EQ is greater than 1, then it means superheated. Superheated vapor. Okay. Then there is volumetric quality. It is defined as beta is equal to Qg upon Qf plus Qg. Q is the volumetric flow rate, and 1 minus beta is equal to Qf upon Qf plus Qg. And Qf plus Qg is equal to Q, total volumetric flow rate. Similarly, here m dot f plus m dot g is equal to m dot, the total mass flow rate. Mass flux is a convenient quantity. It is the mass flow rate per unit cross sectional area. So, G is defined as m dot upon A, and Gf and Gg are the mass fluxes of liquid and gas phases, and their sum is equal to the total mass flux. Gg is equal to m dot G upon A, and it will be equal to G into X. Gf is equal to m dot F upon A equal to G into 1 minus X. Then the velocities Ug is equal to m dot G upon rho G Ag. It is also equal to Qg upon rho G, and also equal to Gx upon rho G alpha. Similarly, Uf is equal to m dot F upon rho F Af is equal to Qf upon rho F is equal to G 1 minus X upon rho F 1 minus alpha. These relations can be easily derived. For example, let us consider this. Ug is equal to m dot G upon rho G Ag. This directly follows from the mass flow rate, definition of the mass flow rate, and m dot G upon rho G is equal to Qg. So, we can write it as Qg upon rho G, and m dot G upon Ag, Ug is equal to m dot G upon rho G Ag. So, we can write it as m dot G upon rho G A into A upon Ag. Now, m dot G upon A is nothing but Gg, the mass flux of the gas phase. So, we get Gg upon rho G, and Ag upon A is alpha, and then Gg is equal to Gx. So, we get Gx upon rho G alpha. Similarly, this other relation for Uf can be derived. Then There is another quantity called superficial velocity. Or it is also called volumetric flux. It is the volumetric flow rate per unit area, and the volumetric flux of the gas phase is the volumetric flow rate of gas phase upon the total cross sectional area, and similarly the volumetric flux of liquid phase is equal to QF upon A. So, Jg plus Jf will be equal to the total volumetric flux J. Now, from this we get some relations. Jg is equal to Ug alpha is equal to J beta, and it is also equal to Gx upon rho g. And similarly Jf is equal to Uf 1 minus alpha is equal to J 1 minus beta, and it is equal to G 1 minus x upon rho f. These relations can be derived easily. For example, this Jg is equal to Qg upon A. So, we can write it as Qg upon Ag into Ag upon A. Okay. And Qg upon Ag is nothing but Ug, and Ag upon A is alpha. So, it is equal to Ug alpha. Now, Jg is equal to Qg upon A. So, we can write it as Q upon A into Qg upon Q, and Q upon A is J and Qg upon Q is equal to beta. So, it is equal to J beta. Jg is equal to Qg upon A, and we can write it as m dot g upon rho g A, and m dot g is equal to m dot x and m dot upon A is equal to g. So, this is equal to Gx upon rho g. So, this way we can find relations between the different quantities that we have defined. Some more relations are Gg is equal to Jg rho g, and it is also equal to Gx. Gf is equal to Jf rho f, and it is equal to G 1 minus x. Okay. So, now to derive this Gg, it is equal to m dot g upon A, and m dot g is equal to Qg rho g, and Qg upon A is nothing but Jg. So, it is equal to Jg rho g. Similarly, the other relation Gf is equal to Jf rho f can be derived. Now, there is an important quantity called slip ratio. it is defined as the ratio of the gas velocity to the liquid velocity. Generally, in two-phase flow, the two phases move with different velocities. Sometimes we assume that they move with the same velocity. In that case, slip ratio is equal to 1. But usually the velocities are different, and commonly the velocity of the gas phase is higher than that of the liquid phase. So, usually slip ratio is greater than 1. This slip ratio is equal to m dot g upon rho g Ag upon m dot f upon rho f Af. Okay. So, we can write it as m dot g upon m dot f into rho f by rho g and into Af by Ag, Ug by Uf. Okay. And m dot g by m dot f is nothing but 1 x upon 1 minus x, and then we have rho f upon rho g, and this Af by Ag is 1 minus alpha upon alpha. Okay. Now, we can rewrite this relation as follows: 1 minus alpha upon alpha is equal to 1 minus x upon x to rho g by rho f into Ug by Uf. This is called the fundamental White quality relation. Sometimes we use specific volume in place of density. Specific volume, it is denoted by V. So, Vg is equal to 1 upon rho g and Vf is equal to 1 upon rho f. Then there is this delta T sat, the degree of superheat is given by T minus T sat. The subscript sat refers to saturation. T sat is the saturation temperature at a given pressure, and T minus T sat, which is denoted by delta T sat, is called the degree of superheat. This occurs usually in boiling problems, and in case of condensation, the temperature is below the saturation temperature. So, we define a quantity called delta T sub, degree of subcooling, which is T sat minus T, degree of subcooling. Okay. Now, pressure gradients. dP by dz. Remember, z is the axial coordinate, because the symbol x we are using for quality. So, we are not using x for the axial coordinate, we are using z for that purpose. Now, dP by dz is the pressure gradient in the axial direction. But in two-phase flow, the pressure gradient has three contributions. One is the pressure gradient due to friction and pressure gradient due to acceleration plus pressure gradient due to gravity. Okay. The suffix capital X refers to friction, suffix A refers to acceleration and suffix Z refers to elevation or gravity. We will be deriving this equation later, which comes from momentum balance. Now, in two-phase flow, there are several types of pressure gradients which can be defined. There is dP by dz capital F, small f. This is the pressure gradient that would have occurred if only liquid were flowing through the channel. That is, if we ignore the gas phase and we assume that only liquid is flowing through the channel, and based on that assumption we calculate the pressure gradient, which will be hypothetical pressure gradient. So, that will be this pressure gradient. So, for a circular pipe, it will be equal to 2Ff upon d Gf upon rho f. Okay. Where Ff is the friction factor, which is calculated based on the assumption that only liquid is flowing through the channel. We can rewrite it as 2Ff upon d into G square 1 minus x whole square upon rho f. Or 2Ff upon d G square 1 minus x whole square Vf. Then there is another pressure gradient which is denoted by dP by dz capital F, Fo. This is the pressure gradient which would have occurred if all the fluid were in liquid phase. This is different from the previous one which we have defined just now. Assuming that only liquid is flowing is different, and assuming that all the fluid is in the liquid phase is a different assumption. Here we take the total mass flow rate or the total mass flux and assume that everything is in the liquid phase, and based on this assumption we calculate the pressure gradient, and which will be surely hypothetical pressure gradient, and that is what this pressure gradient is. So, it will be equal to 2Ffo upon d into G square upon rho f. Here we take the total mass flux G, and Ffo is the friction factor that is evaluated based on the assumption that all the fluid is in the liquid phase. So, this will be equal to 2Ffo upon d into G square upon rho f, also equal to 2Ffo upon d into G square Vf. Then similarly we can define dP by dz G, which is the hypothetical pressure gradient that would have occurred if only gas were flowing through the channel, and dP by dz GO is the pressure gradient that would have occurred if all the fluid were in gas phase. But these pressure gradients which we have defined, these are not the actual pressure gradients. These are hypothetical pressure gradients. For the actual pressure gradients, we will use the following notation: dTp by dz FF. This is the actual pressure gradient due to friction in the liquid phase. And dP by dz GF is the pressure gradient due to friction in the gas phase. Now, how do we calculate FF and FFO, FG and FGO? For that, we define the different Reynolds numbers. REF is the Reynolds number assuming that only liquid is flowing through the channel. So, it will be equal to GFD upon mu F. So, it is equal to G 1 minus x into D upon mu F. And REFO will be equal to GD upon mu F. Then similarly, we can define REG and REGO will be equal to GXD upon mu F, and REGO will be equal to GD upon mu G. Here also this is mu G. Then from this Reynolds number, we can calculate the friction factor. So, friction factor is a function of Reynolds number, and it is equal to (16 by RE) for laminar flow. And for turbulent flow through smooth pipes, it is given by 0.079 Reynolds number raised to minus 1 by 4. This is called the Blasius relation. There are some more relations for friction factors, and there are relations for turbulent flow through rough pipes also, but here in this course, for simplicity, we will use the Blasius relation. Now, the friction factors which we have denoted earlier, FF will be equal to the function of REF, and this will be equal to either 16 upon REF or 0.079 REF raised to minus 1 by 4, depending on whether it is laminar flow or turbulent flow. FFO will be function of REFO. It will be equal to either 16 upon REFO or 0.079 ReFO raised to minus 1 by 4. Similarly, Fg is function of Reg. In a similar way, we can correlate, and FgO will be function of Rego.